can you hear me online? Yeah. Okay. Yeah, welcome everybody to today's lecture in the series of the RIG lecture series, the lecture series of the Robotics Institute Germany. So my name is Tamim Asfour. I'm professor at the Karlsruhe Institute of Technology, and today I'm going to talk about robot learning from human demonstration, a very exciting topic, a new way how we should program robots in the future, and in particular, it will be about learning knowledge or task models for manipulation. Just a brief introduction to what we are doing here. Can you maybe remove this one? Yes. Barbara? We have been developing humanoid robots here at KIT. You see here the ARMA robot family. We started 25 years ago, and now we released last year the 7th generation of our humanoid robots. And what these robots are actually doing can be seen also here in some of the videos, some household tasks where we expect that these robots soon will be able to perform that in different environments, at homes, nursing homes, retirement homes, in order to contribute to a longer self-determined life of humans. You see here the robot in the kitchen environment, the robot here performing manipulation of deformable objects, preparing dinner, loading the dishwasher, and so on. But humanoid robots are actually multi-purpose machines. We are not developing a special machine to perform one single task, but to develop machines which are able to deal with a wide variety of tasks. And you see here some examples where these humanoid robots are performing tasks in more industrial-related environments, like repair and maintenance tasks, like decontamination tasks. These are tasks which are performed usually by humans. These are difficult tasks, sometimes dangerous tasks, and dirty tasks. And we believe that robots actually should, at one day, the sooner the better, perform these tasks so that we provide meaningful jobs for humans. So in our research, we tackle actually 3 research areas. We work on the engineering of these systems, really building these systems from scratch, the hardware and the software. We work on the development of methods which allow us to endow these robots with advanced trusting and manipulation capabilities, and also methods which allow us to teach these robots in a very intuitive way. So this means learning from human observation and from experience. In collaboration with colleagues here at KIT, in particular Professor Alex Weibel, we work also on the natural interaction between humans and robots so that we can communicate with robots in natural language. And the topic of this talk today is actually in the 3rd item here, learning from human observation, and in particular here for manipulation. And this is the structure of the lecture. I mean, if we talk about learning from humans, this means we are interested in deriving models which can be transferred and applied to robots, deriving these models based on the observation of the human. And you see here the structure of the lecture. We are not going to cover, we are going through the core concept of learning from human observation, but by far in 90 minutes, we cannot address all specific things. The idea is to give you an overview about what are the core problems in learning from human observation and how can we address them, what are the current challenges. And at some point, when it comes to generalization, we will see specific algorithms or methods what we developed, for example, for understanding of human demonstration. But let's start with the introduction. This is a video actually which tell us about the power.
I'll show you this. Ready? Watch this. Dr. Andrew Meltzoff is trying to clarify just how the baby
Andrew
human learns to
Metzler
communicate.
was demonstrating a task for a baby, as you
18-month-old
see.
Emma watches Dr.
And
Meltzoff play with a series of
what the
objects.
video actually
He,
tell
in
us.
turn, observes what she does with them.
Okay, this is here.
Emma copies the action.
Good job.
This experiment demonstrates the ability of children to learn how to use objects from,
For this study, Dr. Meltzoff
in
has
particular,
purposely chosen
from a very
he has
limited
never
number of
seen
them.
before. They require
In the task was
unusual actions
demonstrated
to make
once,
them
and the
work.
baby was able to reproduce this task in a perfect way.
Even
And
though
of
the
course,
objects
the
get
tasks which were
stranger and
selected
stranger,
here, they should
Emma
be new
imitates the
for the
action
baby. So
exactly.
tasks which you have not done before, and this is the true imitation learning, the ability actually to be able to replicate complex tasks and new
Dr.
tasks
Meltzoff
based
believes
on
that
a very small
imitation
number
is the
of
first avenue of communication
demonstrations, and
between
this is one
adults
of the
and
biggest
infants.
challenges in learning from observation. When we talk about imitation and you go to Wikipedia, you see that imitation is an advanced behavior where individuals observe and replicate others' behaviors. This is not another important thing. Imitation is also a form of social learning that leads to the development of traditions and ultimately our culture. It allows for the transfer of information in our case between a human and a robot, behaviors, customs, and so on, and between individuals and down generations without the need for genetic inheritance. And the word imitation can be used, of course, in different contexts. We're using it in the context of robotics, that robots watch humans, observe humans, and learn from them and imitate the task or the goal of the task, but also in other contexts like animal training or in politics, right? And the question is now, how can robots learn from watching humans? You see here two examples where a robot is watching how a human is wiping the table, and the goal is to learn a model which allow robots to do the same, to wipe the table, to wipe different tables or different surfaces. And the goal of learning from human observation goes beyond the replication or the copying of the trajectories what are demonstrated. So for the successful execution of a wiping task, it's not only the shape of the trajectory is important, but other important constraints for the wiping. The contact constraints with the surface are important. The forces which you have to apply on the surface to remove certain dirt are also important. So we have to keep that in mind. This means the task models, what we are aiming at, they require an understanding of constraints, in particular in this task, contact and force constraints. You see here another example where we would like to learn a task model, and this task model should include preconditions and post conditions for actions. What are things which should be fulfilled before starting to execute an action? I mean, it doesn't make sense to start pouring if the cup, for example, is empty. And therefore, it's important to identify the preconditions and post conditions of actions, to identify what are the relations between objects, that for the pouring, the opening of the bottle should be above the opening of the cup, for example. And it is also very important to be able to recognize that certain actions what a human is performing, what the teacher is performing, are already known. And other actions are new and should be learned and should be added to the knowledge base of the robot. Therefore, not only contact and force constraints, but semantic and symbolic information should be extracted from the demonstration, in addition to the sub-symbolic information, the way how we execute certain projects. If you go to the literature, and you start searching for learning from human observation or imitation learning, you will come across different terms. Some people call it learning from or by demonstration, learning from human demonstration, programming by demonstration, imitation learning, and so on. You will see these terms, they are used usually in an interchangeable way. But of course, there is a little bit of difference from my point of view, learning from human observation. This is really, generating knowledge based on the observation of the human, to understand human actions, to do action recognition, for example, and so on. Programming by demonstration should be actually called robot programming by demonstration, is another way how we can program robots based on human observation. So, learning from demonstration is a broad concept. How can robots learn from watching humans? For example, learning to cook by watching a person, you might learn the techniques, the timing, or even why certain ingredients work together, right? I mean, this is not only how the chef cook, move, or perform certain motions, but these are really other important informations which must be considered here. Imitation learning is one approach of learning from demonstration. So it's one way to directly imitate what humans do. For example, here in the cooking example, learning to cook by exactly copying every movement and action what the human makes. So this means we have to move from direct copying of things, what humans perform, to abstract learning of goals and of constraints. And why learning from demonstration or programming by demonstration or imitation learning matters for us in robotics. The first thing, traditional robot programming ways are time consuming, can only be done by experts, and we would like to provide intuitive ways for programming robots instead of manual coding of robots. And this can be done, of course, by non-experts. So expert programmers needed for every single behavior, for every single task would not be needed in this case. And the human learning paradigm tells us, as we saw in the video before, that humans and children actually naturally learn complex behaviors and complex motions through observation and imitation. And this is a fantastic way how we can transfer knowledge between different environments, between a human teacher and the robot. But back to our outline, what are the fundamentals of imitation learning or learning from demonstration? What are the core concepts and what are the key questions what we have to solve? If you look at this example here, like steering the salad, and we would like to learn a task model, which means actually semantic information, symbolic and symbolic and sub-symbolic information from the demonstration, like the timing, like which action should be executed when an action should start and when an action ends. There are many important things what we have to consider in human demonstration. For example, how the human move. Of course, this is important. How the arm move while performing a mixing motion. But maybe also the bimanual coordination. The object should be fixated by one hand while performing the mixing action. The way how we are grasping the objects in order to do the mixing. What's the type of the grasp used in this context? How much force is executed on the tool, for example, or on the object in the hand? And in addition, maybe the gaze of the human is very important. where the humans are looking at during the execution of this task. So there are many things what we have to think about when we talk about learning from demonstration. And the core questions are the following. First is what to imitate. So this means we have to identify, based on an understanding of the task, what are the relevant parts of the demonstration of the human. So if I move this object from here to here, I can do it like this, but I can do it like this, right? Yeah. And you can imagine that these parts of my demonstration are actually not relevant for achieving the target goal where I would like to place the object. So what are the relevant aspects of the demonstration? The question is, the second question is how to imitate, yeah? So this means if our goal is to prepare the salad or to move the button from position A to B, this is our abstract goal. We have to transfer this abstract goal into motor commands, yeah? We have to map actually the goals. We have to map these abstract goals to motor commands, which would lead to a motion of the robot. Another important question in imitation learning is who to imitate. This is the problem of the selection of the teacher. I mean, robots are still very stupid machines, right? If you have two people demonstrate doing something in front of the robot had actually, or should be able to identify the right teacher. Who should I actually imitate now? Should I imitate her or should I imitate him? And of course, the when to imitate. What's the right point to start in time to start imitation? This is the so-called temporal segmentation chart. If we are interested in now building data structures or building knowledge for robots based on from watching humans or from observing humans, we can come up with a kind of conceptual architecture. You see here that we have basic skills. This is also inspired by biology, that humans have basic primitives, movement primitives, which are combined in order to perform complex tasks. And the question is now how to learn, for example, these famous libraries of movement primitives. In order to do that, we have, of course, to observe humans. We're talking about learning from human observation. And as you will see in this lecture, it's not only the motion of the human is important, but really the motion of the human in relation to the objects which are involved in the task. And therefore, we need to perceive both the motion of the teacher or of the human and additional information about the objects which are involved in the task. In particular, spatial information about the relations, for example, between the hand of the human and the target object. Of course, if we learn these primitives from human demonstration, these are in the space of the human body, we have to map them to different robots. We are not only interested in programming the AMA humanoid robots, but would like to use the same concept in order to program any industrial robot, for example. And we know here that there is differences in the kinematics, yeah, of the two bodies, of the human and of the robot. And therefore, depending on the space in which we learn these primitives, we have to solve or to map actually these primitives to the target system. If we are learning, for example, in the Cartesian space, the human demonstration, and would like to map that also to the robot in Cartesian space, we have to solve the correspondence problem between the two kinematics, because we know the kinematics of the human body and of the robot, they're not the same. But if we look at that, actually, there are many research questions what we have to solve. First of all, we have to be able to recognize actions or movements, so movement recognition, in order to learn these elementary actions, what are called movement primitives. And this is done by techniques of segmentation. This means we have to decompose the demonstration in important segments, which can serve as the basis for learning. On the other hand, we have to generate motion for the robot, as I mentioned before, by mapping what we learned here in the library, or the representations of the movement primitives in the library here, to the target system, to the kinematics of our robot. This is motion generation. Of course, even if we learn in the movement primitives in the configuration space, and we have a robot with a different configuration space, different number and arrangement of degrees of freedom, we have also to do actually this map. The third important question is, we would like to also continuously adapt the learned knowledge based on experience, right? If the robots learned a skill from human demonstration and executed, and the execution was not perfect, the robot should be able to improve and adapt the learned knowledge based on this experience. This is a research question where we are done in the area of reinforcement learning, as you see. And last but not least, we are, of course, interested in keeping the amount of elementary actions or primitives small enough. We are not interested in learning a new primitive for every new single motion that a human perform, and therefore we have to be able to recognize similarities between things which we learned already and things which are demonstrated by the teacher. This means this is actually a problem of action recognition, what we have also to address. And I didn't talk about the problems which are associated with the perception of the human demonstration, with the perception of a human, and with the perception of the object, which is, of course, another challenging problem from, for example, computer vision point of view. So the question is now how we can learn these library of primitives. Yeah, you saw that on the slide before, and our goal is to build this library based on human observation. You see here different primitives like move, grasp, shift, push to the left or to the right, or slide to the left or to the right, or wipe the table, and your complex tasks like prepare a dinner or prepare the salad are composition of these primitives, right? Like cut, pour, mix, and so on. And the key question is actually how should we represent these primitives, yeah? And how we should adapt the primitives what we learn from demonstration. So given here demonstrations of the human, we have somehow to analyze these demonstrations, and in order to build this library with the primitives, we would like to store, or with the primitives which should be stored and should be used in a different context. And this is not an easy question, actually, because I mentioned now recognition of similarities between primitives so that we don't add new primitives which are similar to things what we know, but there's more than that. Yeah, in the recent work, we are exactly addressing this question, and we identified fundamental operations what we have to perform in order to really build this library. Of course, we have to be able to add new primitives. If a demonstration is completely new, we have to add something. We have to be able to improve existing primitives based on experience, but also to remove primitives which we never use, or where the execution of these primitives led always to failure. Maybe there are some primitives which happen all the time together. It's better to merge them and to combine them to one single primitive. This is the merging, or the opposite. It might be more useful actually to split the primitive into two because of many other things. And this merging and the splitting can be done based on spatial information, but also based on temporal information. If you are interested in these details here, in particular, how such movement primitive library can be learned incrementally. Incrementally means that this updates or these fundamental operations are executed without really the need of without the need for storing all demonstrations. If you are interested in that, a recent publication from last year here described that in more details. But let's move further. We know now about the key questions and the core concept of learning from demonstration. But let's look a little bit in more details about how a cycle for learning from human demonstration look like. I hope you understood so far that we have to observe humans and we have to observe not only the motion of the human, but also the motion of the objects. And we have to build generalized representation, which allow us to transfer the learned knowledge to different contexts, right? If I learn to pour from an object into another object, I shouldn't learn again to do the pouring task with two different objects. So this is crucial and important. So we are interested in learning generalized representations of actions. And more importantly, we are interested in learning the constraints of the tasks. Because I believe the constraints of the task are crucial and they are fundamental for generalization. If we understand what are the constraints of the execution of the task, the constraints of the task of wiping is to have contact with the environment and to adapt the forces. And if we learn these constraints, we can generalize to wiping of any surface, right? And of course, the last part is what we learn should be reproduced on a robot. I call it reproduction, where we should evaluate success in order to improve what we learn based on the execution, learning from experience, and in order to update the underlying models, underlying model of our primitives, for example, to merge primitives or to split primitives, or the underlying models which we are using for generalization or for learning task constraints, or the underlying models which are used for human observation, for tracking of human observation. So I think this combination of data coming from human observation, prior knowledge, what we have about models, how humans move, how robots move, whatever, how constraints maybe can be described, the combination of that is crucial and important. And we'll go step by step through this imitation learning cycle. We'll start by observation. And this is, of course, a task what we have to solve anyway, because we would like to capture human demonstrations. And as I mentioned before, it's very important to capture the motion of the human and the motion of the objects involved in the task. And this is important because the human motion tells us about what actions to imitate, right? And the object motions tell us about what action effects actually do. What are the consequences of actions and the post conditions of actions which should be considered in our image. And you see here many things. I think this is very obvious for master students interested in robotics, right? That when we capture the motion of the human, the full body pose is important, the hand gesture, the end effector trajectory could be important, or the pose of the objects, 6D pose, how the objects, the dynamic properties of the objects. And in order to do that, these are tasks actually which are related where we are in robotics, of course, profiting a lot from computer vision community, and where we know there are different ways how we can capture human demonstrations. Human demonstrations means the motion of the human and the motion of the objects involved in the demonstration. This can be, for example, now classified in two ways. We can, of course, attach markers to the objects and to the human. This is what's done in the biomechanics community all the time, where you attach markers to the human body to understand human motion. You can attach different type of markers, like passive, active markers, IMU-based markers. The same can be done with objects. Or, of course, the use of purely markerless systems, like cameras, RGB or RGBD cameras, And recently, deep learning approaches provide a very nice tracking and pose estimation of human pose and of objects. And you see here some examples. This is what we are doing in our work here. We are collecting mock-up data of human demonstrations in daily tasks, not only actually single arm or bimanual manipulation, but whole body action, local manipulation actions. And we are mapping this to a reference model of the human body. What you see here, mapping both the motion of the human and the motion of the object using the, of course, available models of these objects. But and we have a wide variety. We have one of the biggest biggest worldwide publicly available mock-up database. As you see here, used also recently by other groups or a subset of larger data sets which are used in the computer vision community. And you see here the variety of the tasks which are collected and where you can actually access this data and use it in your research for whole body actions or local manipulation actions, and in particular here a new data set for bimanual manipulation action. But this is not important. We are talking about observation in the context of human learning from human demonstration. The one example was now on mock-up data and the data sets which are available. You see here a more recent example where we are using RGB data, depth information, in order to get the human pose and to do the retargeting to a reference model of the human body, which is an interface to our robots and should be interfaced to other robots in the future. So the second important part is, of course, generalization. I'm not saying that observation is not important. Observation is important and very crucial. And think about now capturing the configurations of the human hand from visual data. I mean, this is very, very difficult task. This will be the goal, that we have robots which will understand everything what we do and learn incrementally from demonstration. So observation is very crucial and very important, but this is a topic which is now not the core of this chapter. If you are interested, you can visit the lecture Robotics 3 where we talk more about these things. But the most important thing here is in learning from human observation is generalization. And before starting talking about generalization, and as you see here, I would like to talk about learning skills from human observation and generalized skills from human observation versus learning task models. Yeah, you will see the difference soon. Then we'll talk about how we decompose human demonstrations in smaller pieces, which we can represent, for example, as movement primitives. And finally, we will talk about constraints, how we can learn from human observation constraints which represent the task we are interested in. Yeah. And if we have time, we'll talk about reproduction, but I know we'll not have time to talk about reproduction today. So let's start with generalization. So learning generalized representations of actions and learning task constraints. And this will be the major part of the lecture today. Generalization means decomposing the demonstration into smaller pieces, right? This is the one thing on a trajectory level. This means segmentation and then the representation of these pieces in a way which is parameterized. So from a mathematical point of view, if we draw a trajectory and we would like actually instead of the data points of the trajectories to have a model which we can adapt with two parameters like start and end point, and then the function or the approximation tell us how this can be done. I mean, this is what we are interested in. But the generalization, I would like to emphasize that the generalization must happen or can happen on two levels. The first level is generalization on trajectory. where I have really several examples, of a trajectory, how humans perform cooling, for example, and somehow I build an average and I come up with a mathematical model which describes these trajectory, distance sample or trajectory. But the more important part of generalization on symbolic level. This is really understanding not only the motion, but understanding the actions which are needed for the task, the sequence of the actions, and the constraints, preconditions, and postconditions of the actions. So, and let's start with the first one. And this is very nicely explained in the Handbook of Robotics. You know, the Handbook of Robotics, here, the second edition, there is chapter 74 in the book, is about learning from human demonstration. And the distinction here between the two levels of encodings or the two levels of generalization. The first one is trajectory level encoding, or it's called also subsymbolic representations. This means we are interested in learning a low-level representation of a skill as nonlinear mapping between sensory input and motor output. Yeah. So we have a demonstration. Unfortunately, I don't have my tablet to draw on it here. I forgot that. We have a demonstration, and this demonstration is continuous motion, independent how we capture it, with mock-up data or with mock-up systems or from RGB or RGBD data. So this data is usually projected in a latent space of the motion. So we get the latent representation of the trajectory of the motion or the demonstration at the trajectory level. This means actually a kind of averaging of the trajectory. So we extract an averaged trajectories with different variations, so that this averaging or this approximation actually of the demonstration can be applied or modified and applied to new contexts. For example, new start and end goals of the trajectory. So it's only about motion, how we can approximate actually trajectories and how we can represent these trajectories in a parameterizable way. The second level is the symbolic level encoding. This means, as I mentioned before, we need this is a high-level representation of a skill of a demonstration, which decompose the demonstration in a sequence of action units. Yeah. So this means preparing the salad. We will the extraction of this symbolic information for the task means, oh, grasp the knife, grasp the salad, cut, put it in the bowl, pour olive oil, mix, right? These are the actions we are interested in, on this level. As you see here, cut, mix, pour, and so on, this is a lot of knowledge what we need. So we have to be able to recognize that the human is doing this thing, these things. And this is actually reflected in this prior knowledge here, where we have a predetermined set of controllers or of actions or primitives, which can be used in order to generate a symbolic representation of the task based on the extracted or the recognized actions in the demonstration. I can only recognize actions I know, right? Or I can recognize that an action which is demonstrated now is unknown action, but this is the important prior knowledge. This is, for example, the movement primitive library, which we have to provide to the system so that the system can build these symbolic representations. Generalization means that we have to extract not only the actions which were executed, but really the structure of the task. The structure of the task in terms of also the temporal relations to actions, between the different actions or between the different primitives. So to summarize, trajectory level generalization means generalization of motions, generic representation of the motion which allow encoding different types of trajectories. This addresses the question what's important to imitate. And of course, this does not scale up to reproduce, for example, complicated skills or complicated tasks. Yeah. Symbolic level generalization means we have a sequential organization of predefined actions or elements, and this allows us to learn hierarchies, to learn rules which are important for the task. Of course, we need prior knowledge, as you see here. Maybe current progress in large language models and so on will tell you we can learn this from scratch, but also these large language models are prior knowledge, actually, what we need. So we need prior knowledge to predefine symbolic representations of actions, and we need to predefine a set of basic controllers or basic primitives for the reproduction. In both cases, we have to decompose the demonstration in different parts, right? We have to do a segmentation on the trajectory level, but also on the symbolic or on the task level. So maybe before I continue here, we can take some questions. Usually I have a 7 minutes break in the middle of my lectures. So if there are any questions, I can answer them now for this first part. No question? Yeah.
Well, maybe this might be answered in like the latest chapters, but do you usually prefer in practice doing actions in joint space or partition space if you want to teach the robot and like a new behavior?
Yeah, this is actually a very important question. The question was, just to repeat the question, whether this learning is done in the Cartesian space or in the joint space of the robot, right? This was your question. I would say it's done, you can do it in both ways, right? I mean, if you can capture the trajectories or the joint angles of the human body, then you can learn movement primitives in the joint space. If you cannot, you can only capture the tool center point, for example, or the hand of the human, then it makes more sense to learn these things in the end effector or in the task space. And it is done in both, actually. I mean, people are working on both things, including ourselves, and this depends on the task. But if we are interested in goal-oriented actions, like we have to reach really a goal in order to do pouring or cutting or inserting and so on, task space representations are the suitable way, the right way to go, yeah, because they allow for a better generalization, yeah. But this does not exclude also learning. I mean, we learn in the human space. You saw here this database. What we have, we learn also movement primitives in the joint space. If it is about whatever waving, about generation of the human-like motions, for example, this is easier than solving always the inverse kinematics in order to generate a configuration when you learn or when you study data in the task space. Okay, then we will continue. If there are no other questions, segmentation of the demonstration. And segmentation means to divide a motion into meaningful segments. This means actually to identify the prominent and distinctive points in the demonstration. And I will call them key points of the demonstration, yeah? The easiest way, I mean, if you have a trajectory and this trajectory has minima and maxima, of course, the minima and maxima might be the important key points which we should consider for our generalization. So this means actually, as examples, the end of the reaching phase of grasping could be where we establish contact with the object. could be a key point, or a single step of a walking motion, yeah, when the next step, when a step starts or ends. Meaningful depends here on the application and is very subjective. For example, is meaningful segmentation, or should we segment every single step in walking, or should we segment only the transitions between different walking styles, from running to walking or from running to jumping? So you see here, it's not easy actually to define this concept of key points. Input data, what's used, joint angle trajectories must used for that, Cartesian trajectories, and also semantic relations between objects and hands. Yeah, not only really the joint space and the task space, but also the semantic relations between the objects and between the hands of the demonstrator. And I will here describe one approach which do the semantic segmentation of the task based on the relations. In particular, based on the change of relations between them. And this work is from the group of Professor Florentin Golgota here, learning the semantics of object-action relations by observation. And the idea is really simple and nice and powerful at the same time. So for each action, so we consider only, or they consider contact relation between objects, and these contact relations occur, of course, in the same order for the same actions, right? They do it, this is a conceptual work. I mean, the contact relation is very difficult to detect context in robotics, right? If you demonstrate a task now for me, and I have to figure out whether you have contact with your cup or not, this is very, very challenging and very, very difficult task. But they assume that we can actually detect these contact relations based on visual approach. See here the task, human is, we have a plate, the green plate, and the human is placing an apple here on this plate. And of course, we have different phases here. We have here phases where the objects are not touching each other. Then at some point, of course, the hand is touching the apple, and at some point the apple touches the plate, and so on. And at the end, you see here that the apple and the plate, they are completely over, right? So very, very simple. These relations are extracted here between 2D image segments, yeah, these areas. And they are now considered because, as I mentioned, real contact relations are hard to recognize from approach. But what they did, and this is what we're interested in first, we are interested in data structures, right? These demonstrations of the human must be now put somehow in a data structure which we can use. They said, okay, we introduced the semantic event chain, and this semantic event chain, as you see here, is based on the fact that objects involved in the demonstration are either non-touching each other, this means a zero, or overlapping, like at the end here, or they are touching each other, right? And you see here, these are relations, the rho x, y, this is the relation type between x and y. And you see here at the beginning, the table is object 1, the plates are object 2 and 3, and the apple is object 4. And we see actually that at the beginning, all of them are overlapping. So 3 and 4 and 2 are overlapping. We see here in the second column here of the table, we see that 1 and 4 and 2, they are touching each other, and 1 and 3, they have the overlap relation, yeah, and so on. And we can actually now map this demonstration, the images, into this data structure. You see, we have this matrix here, which tell us about the relations between the different objects involved in the demonstration at every point in time. So what does this mean for us? This means we have actually the relations of each part, if we have a new relation, or we would like to evaluate the relation to each pair of image segments here, we have to add a new column here, right? With more demonstrations, we have to add new columns. Yeah. So, and what's crucial here and elegant in this approach, that the key points of the demonstration, when important things change in the demonstration, they can be detected by looking at the change in the structure of the graph. Yeah. You see here, we have these graphs which represent actually the relations between the objects, the touching, non-touching, overlapping relations. And you see here that every time when the graph structure changes, we have something happen in the demonstration, and this could be important now for the segmentation. And of course, they evaluated that with complex objects. You see here that we have high number, 15, 20 objects here involved in these demonstrations using these 2D images. So the goal is now to learn such a model of semantic event chain, which represent an action by searching for when we learn these actions, and a human is demonstrating now something, we have to only search for similar columns and similar roles in the demonstrations. Of course, we have to identify some similarity measures here, but this, if you are interested, you can go to the paper and learn about that. But this type of segmentation tells us really how things change, but it doesn't tell us anything about how the hands move, right? Tell us about change of states of the world. It's very symbolic, but not really how the hand moved from this to this. What was the motion? So therefore, actually in robotics, this symbolic information is of course important, but we need the sub-symbolic information. We cannot execute things only based on this symbolic information. And therefore, we extended this approach by introducing a second level of the segmentation. We call it hierarchical segmentation based on object-hand relations. And you see here a simple example for grasping a cup and doing something with the cup. And this hierarchical segmentation uses on the first level here, where you see non-contact cup in the left hand and no contact, the semantic event chain what we saw before, where we detect contact relations between the objects and then identify these key points. Here we have only two key points here between no contact and cup in hand, and between cup in hand and no contact. These are semantic segments, yeah, and these are detected based on contact relationships between the object. But we are, of course, if we are interested in building this library, what I talked about in the beginning, would like to know what did the human do actually with the cup? So the human lifts the cup, pour from the cup, and place the cup, for example. Okay, yeah. And of course, in order to create contact with the cup, we have to grasp it. Something what we can infer, yeah. And therefore, the idea is how can we combine the two things? How can we identify semantic segments based on semantic event chain? But how can we identify the important primitives, yeah, like lifting, pouring, placing, retreating, cutting, whatever, inserting also from. And therefore, hierarchical segmentation, the semantic segmentation is based on object relation change, and the motion segmentation is based on the characteristics of the trajectory. And for that, you see here an example how this worked. This was done with mockup data here. In the meantime, we are doing it also with RGBD data. And you see actually here in this diagram on the bottom left that every time when a contact is detected, and for the detection of the contacts here, we're using, of course, the models of the objects, and we're using collision check models. So it's actually, we have meshes of the objects, and the collision checks between the objects or between these meshes tell us something about the contact. So we're able to identify the semantic segments, and now you see here for the second level, when the style of the motion changed, this means the motion characteristic changed, the way how you shape, for example, the bottle. We have a kind of the keyframes or the key points for a new potential primitive what we should learn. So this is another example. You see here grasping a bottle in order, for example, to lift it. Oh, sorry about that. There is a delay here, right? So grasping the bottle here, this means actually this semantic key point, and here placing another keyframe or key point here, which should be considered on the first level. So this is based on a hand-object relation. And on the second level, you see here that we are able to identify these key points here in the demonstration. So all of them actually should be videos, but they are not running here. This one and this one. And so that we can also identify ways of the execution of the motion, by the way, based on the acceleration profiles of the executed motion. But the details, if you are interested on the matrix, what we use in order to do that, you can look into the paper or ask after the lecture. So now I hope we know about the difference between learning skills. This means on symbolic, sub-symbolic level, and learning task models, which include both symbolic and sub-symbolic information. So do we know that? Everybody understood that this is very crucial and very, you are not happy with that, right? Why?
It's not that clear.
It's not clear for you. Okay. Okay. So, but as I mentioned before, and in order to do that, we need a segmentation. In order to learn, or either on trajectory level or on symbolic level, we need a segmentation. And I explained today only maybe one of my favorite approaches for segmentation, but of course there's plenty of works which deal with segmentation on trajectory level, like zero velocity crossing, minima, maxima, hierarchical clustering, and so on. There is a lot of literature on that. It's not the only solution. This is one of my favorite solutions because it combines, or it allows us actually to segment the task on both levels, on semantic level, but also on sub-symbolic level, and it's our own work. Yeah, maybe a little bit of advertisement of our work. We borrowed, of course, a lot from colleagues. Yeah, the original idea is not coming from us, but from colleagues from Göttingen. So, but as I mentioned at the beginning, constraints are important. When we talk about generalization, it's not only about generalization of the primitives and so on, but really about the constraints. And these are crucial and important for understanding of the task. Yeah, and constraints can be preconditions of actions, temporal order of actions, right? Or order of actions and other temporal constraints, for example, which should be satisfied for the execution. Spatial constraints and what we talked about, like object-hand relation, are kind of spatial constraints. But also we have what I call execution-related constraints. Yeah, execution-related constraints like the contact, like the forces, like maximum torques, what should be what are allowed, for example, on a robot, velocities, and so on. And I believe that constraints is, and as many people here, I think Oliver Brock in Berlin, is he here, by the way, Oliver? Or he is not in my lecture? Okay, believe that constraints are crucial, actually, and important, yeah? And The question is now, we would like to learn these constraints from human demonstration, right? Not to define the constraints, to hand code the constraints. We would like to really learn them from human demonstrations. Therefore, the question is, how can we detect these constraints? How can we formulate the constraints? And how can we learn them from demonstration and leverage them for control, for learning and for control? And today here also I would like to present one approach on learning key point-based geometric constraints from human demonstration. So key point-based representations means actually sparse representations, right? That we are representing, for example, complex demonstrations of the human in a sparse way. And here we are talking about geometric constraints, not force constraints, for example, or interaction constraints, but from human observation. Again, here, what do we mean with geometric constraints? There are restrictions based on geometric relationships, like distances, like alignment, parallelism, and so on between geometric entities like points, lines, planes, squares, and so on. And key point-based constraints are geometric constraints between key points attached to object functional parts. Yeah. This means actually such a set of key points can then describe for us the state of an object in a very sparse way. We can describe the state of the object by only few key points, right? And these key points can be used to describe also functional parts of. And you see here two things. Object instances of the same category, they share a common set of key points. For example, all mugs have a handle, an opening, and a body. Yeah. And if we attach now a key point to the opening, to the handle, and to the body, then we have a sparse representation of the state of the object. Or object instances from different categories may share common key points. For example, mugs, kettles, water filters, doors, all of them have handle. Yeah. And this is actually very important and very, very powerful to have sparse representations which can be used to describe the state of an object, but on the other hand, to describe also functional parts of these objects. And there are in the literature several ways how these key points can, key point-based object representation can be created. Of course, by random sampling on the object, this means we have some key points which don't have any semantic meaning. I also put the papers here. You can look into that if you're interested in it. Key points with semantic meaning. This means actually key points which are associated with functional parts of objects. And here I distinguish between three categories: supervised learning of these key point-based representations, where manually you annotate actually the parts of the object. You see here, for example, from the work of the group of Russ Tedrick here, that actually you assign the opening of the cup or the center of the handle here, or the bottom center of the cup here. These are important key points. You can do it, of course, for the shoes. And so you have to annotate key points on objects, and then you have to train a neural network, which will give you the key points, important key points on functional parts of objects. Self-exploration, where you train a reinforcement learning agent. But what I would like to talk about today is how we can actually extract these key points through statistical analysis or statistical evidence. Yeah, this means actually how can we find key points as invariant features in the human demonstration, and we will go and I will explain that with this example of pouring. So we would like to statistically analyze important key points or key points in human demonstration to identify invariant features of the task. And you see here, and as I motivated before, I believe when we learn these constraints, we can better generalize to different objects involved in the same task. For example, here we can generalize to different cups. Here we can generalize here to different kettles, which are used for the pouring. And the general idea here is, if you look at the pouring task here, what's actually important is a key point on the rim of the cup. Yeah, because this defines actually where we should maybe do the pouring. And the other thing is actually how the handle of the kettle is moved. So one key point, for example, on the handle or on the bottom of the kettle. And you see here, if we learn these relations between these key points, yeah, these are again geometric relations between these constraints, then we can generalize to pouring in any cup, actually, from any kettle or from any bottle or from any container, right? So how do we do that? We start by human demonstration. You see here, actually the task is described by the constraints here, that we have here a constraint to this point here, to the frame, to the frame on the rim of the cup, and also the curve here, which describes the motion of the handle, right? How the handle of the kettle moves. Of course, you would like to learn these constraints from different variations of the executions, different variations of the sizes of the cup, and we would like to learn them from as few human demonstrations as possible. Yeah, we're not interested in using now all the data in the web, whatever, in order to learn that. We'd like to have less than 10 demonstrations in order to learn the constraints which are important for pouring or for pressing a button or for hanging a head and so on. So, and what we do here, we do against based on visual information. This is why it's called a key point based visual imitation learning. This means the approach here consider dense sampling here of the human demonstration, identify these candidate points, the local frames which are important, for example, the frame on the rim of the cup, and also the representations to which allow us to align viewpoints. Yeah, because the demonstrations, yeah, they should be they cannot be actually from one single viewpoint. So therefore, viewpoint alignment is crucial and important. And what this approach, KVL, developed, by the way, by Jeff Gao here, one of my postdocs. This approach actually identify the key points. Yeah, the key points, like here we have a point-to-point key point, point-to-point constraint, sorry, K1, or a point-to-curve constraints on the bottom, for example, of the kettle K2. So we identify the key points, we identify the geometric constraints between these key points for the execution of the task, and we learn the movement primitives which are needed in order to execute the task based on human demonstration. Because the constraints, the geometric constraints, are only symbolic information, but we'd like to learn actually how to move from here to here. And this is done jointly. The approach extract the key points, the geometric constraints, and the primitives which are needed for the execution. And as mentioned, the last part is done, of course, the reproduction of what we learn on a robot, and to show that we can generalize to categorical objects. I don't know how much time I still have, because I have the feeling I will not manage to finish my 70 slides. But maybe we can go step by step. These are the human demonstrations for the pouring task. You see here pouring at different positions in different cups. We have shape variations, we have voice variations. And what's done here We have a novel object representation, so a neural descriptor based canonical space of the objects, dense correspondence detection and local frame matching, transfer of the constraints and the motions. In the second step, we have the extraction of the key points between the constraints, the geometric constraints between the key points. And the last part is the evaluation of the approach. And I hope I will be able to finish that. So here what we do, as mentioned, we combine two models, Dino model for extraction of semantic features in human demonstration. The input is visual information, and stable diffusion for the extraction of geometric features. And you see here these neural descriptors for canonical objects, which we define for the kettle, for the cup, whatever, and the target object. This is a different object actually we would like to use here. You see here the real objects are shown here in the middle. And we detect these point correspondences between the objects based on this representation and based on a cosine similarity measure. In the next step, we detect dense correspondences between of candidate points between the canonical object and the target object. These are two different objects. You see them. I mean, the difference is, I hope the difference is it's not the same object. And we can, since we know the local frame on the canonical object, we have to only do a kind of matching of this local frame on the canonical object to the target object, and to estimate the position actually of this local frame, because this is very, very, very important here, the position of the local frame, for example, for the cooling and the alignment of the view. How we can transfer the constraints and the motions, we express the points and their constraints and motions relative to the local frame on an object part. Yeah, as you see here, if we express that in this way on the canonical object, we can transfer that from the canonical object to the target object, which should be, of course, from the same category, yeah, to another categorical object. And we transfer also the gross pose, yeah, from the canonical object to the target object, so relative to the object part. The object part is the handle here, and you see we have two different handles. We have to do also this transfer for the grasp pose. This was too fast, but let me continue. Yeah. Key point based geometric constraints. Again, this is the input. These are the dense candidate points and their trajectories, what we can generate from every demonstration. You see we have also tracking of the hands and tracking, of course, of the candidate points on the object. And what's done first is to align all candidate points, what we get from the multiple demonstrations. You see here, these are these candidate points. This is the hand on the handle, yeah, of the kettle. This is the cup with the local frame at the rim. And what you will see soon, you will see actually here from what we get from statistical analysis, you see here the key points on the handle of the kettle from 8 demonstrations. Yeah, every color is related to another demonstration, and with that we can extract now the local frames, the key points, and the constraints based on statistical analysis that you will see on the next slide. And then come up with this representation that this pooling task is actually, or for this pooling task is this point-to-point relation at the local frame cup rim is important, and this point-to-curve constraint of the handle is important for the execution of the task. So this is actually how this is extracted. I don't think that I can go into the details here, but the details are described in this paper if people are interested. We have two different types of constraints, the linear constraints, which are easily extractable using principal constraints estimation. And the more difficult ones are nonlinear constraints, where a principal constraint estimation is here applied in order to extract these geometric constraints. But in summary, we have 6 types of constraints. You see here the linear constraints like point to point. Pressing the button is, for example, only a point to point constraint. Point to line constraint or point to plane constraint. We saw the point to curve constraints during pooling. These are the nonlinear constraints here, or the point to surface constraint, which are extracted here by nonlinear PCA, principal manifold estimation. And of course, the 6D pose, which is important for grasping, and we need also the 6D pose, which is also done by Gaussian and others. So, in summary, again, the 3 linear constraints and the 2 nonlinear constraints. And I would like to go to the final part. Sorry, this is a repetition. To the final part, which is the evaluation, where we evaluated this approach for extracting of geometric constraints between key points. So key point-based geometric constraints on 6 tasks. Yeah. Press a button, fetch a tissue, hang a hat, insert a stick, clean the table, or pour water. And you see here from 1 to 11 demonstrations, the types of constraints which were automatically extracted. Yeah. So this means for press the button, after 3 demonstrations, we converged to only a point-to-point constraint. So the 3rd demonstration, we still had a point-to-line constraint, but you see here, with more demonstrations, so after the demonstration 4, we converge to point-to-point constraint. The same here for fetching a tissue. If we take here pour water, you see here that we need 8 demonstrations to converge to a point-to-point constraint and point-to-curve constraint, as I explained before. And this not only here this evaluation, but it was also executed on the robot with different kettles and different cups. And you see here and different poses, how these constraints are used in order to perform the pooling task in different cups at different sizes, different locations with different kettles. Nice step forward, right? This is the summary of the algorithm, and in the meantime, we could actually extend this algorithm to bimanual. So this means we know in bimanual manipulation we have some coordination patterns between the 2 hands, like loosely coupled actions, tightly coupled geometric actions, uncoordinated bimanual actions, uncoordinated unimanual actions. And we are able, from a small number of demonstrations, less than 10, to actually automatically detect the constraints, like point-to-point and point-to-curve constraint. You see here in this task where the left hand is holding a cup and the right hand is doing the pulling. This means we have 2 point-to-curve constraints here. Yeah. We are able to extract these geometric constraints and to automatically also extract the coordination pattern, the suitable coordination pattern here, which tell us which coordination between the both hands is used in this task. For example, here, this is a loosely coupled coordination, because the hands, they have to, or both hands have to meet at some point in order to do the pulling. But there is no exchange of forces between the 2 hands, which is the category of tightly coupled bimanual action. And you see here also the execution on the robot here, like placing something over something with 8 demonstrations, or coordinated tightly coupled where you manipulate a tray here with both hands, or uncoordinated bimanual actions, or uncoordinated human workers. So, as I explained, manipulation. So, 10 more minutes. Okay, but for the Karlsruhe people, it's already okay. Manipulation is about understanding constraints. We agree on that. Many people in the community, and the questions what I raised before about how we can detect these constraints, how we can formulate them, and how we can actually use them, right? And I showed two examples today. For the segmentation, the object-hand relations, contact relations, for example, for segmentation, this is a kind of geometric constraint, and also the key-point-based abstraction of geometric constraints and manipulation with the key-field approach. But what we are doing in our work, actually, we developed several taxonomies which describe manipulation. Yeah. And as we know from literature, you know that from Introduction to Robotics, for example, we talked about grasping taxonomy. In other lectures, we talked about whole body local manipulation taxonomies. And these taxonomies, of course, they are rigid structure, but they are actually kind of frameworks which allow us to categorize things, right? To classify things. It's a kind of a space which describes for us the possible constraints. Yeah. And what we did, for example, here, taxonomy for bimanual manipulation, which tell us something about the coordination patterns between the two hands. Like the pulling is actually loosely coupled coordinated bimanual action, while moving the plate here with both hands is a tightly coupled because we have force interaction between both hands and they are moving in a symmetric way. But when you do mixing, you have also tightly coupled coordination pattern, which is asymmetric, where one hand is dominant and the other hand has to follow, right? And this kind of taxonomy actually describes constraints, right? What I just explained. I mean, coordinated tightly coupled means actually we have force constraints between the arms, or uncoordinated or coordinated loosely coupled, we have some geometric constraints like what we saw in the KDL approach between the left hand and the right hand. These things were developed independent of each other. But the point I'm trying to do, to make here is that these maybe rigid representations of things, these are conceptual representation, right? Can be very useful in order to bootstrap learning of constraints from human demonstration for manipulation. We have also another taxonomy what we developed, which describe actually whole body poses. And this taxonomy is based on contact between body parts and the environment. Yeah, whether only the body is in contact with one foot here with the environment, like in 1-1, or with two in 2-3, and so on. And again, here this is a taxonomy which describes constraints between the agent, the robot, or the human here, and the embodiment. And in this case, it's of course the contact information, whether there is a contact between a body part or between a body part and the environment. And the questions now for you, actually, as a self-test, many questions actually. I mean, or three questions, not too many, 3 questions, which I selected. In all these examples, what I gave today, we were only dealing actually with rigid objects, cups, kettle, and bottle, and so on. And now think about the task. Imagine you have the task to learn a task model for a robot for folding your t-shirts. Yeah. So this means actually we are manipulating deformable objects. It's a very, very, very exciting and very challenging research area here, which is the unique challenge for learning such a task model for manipulating deformable objects. And this learning should be done from human observation. And what are the constraints which are the most crucial? I mean, I don't have accurate answers to that, yeah, but think about what are actually the most crucial constraints for learning task models for manipulation of deformable objects. And the second question is, think about why actually object relations is important for learning from humans in particular, or in addition to human motion and object motion. Why this is crucial, and give examples of a manipulation task where object relation provide essential information. And I would be always interested in examples where object relation are not needed. Yeah, I'm trying to give you a few things to think about later today and during the Christmas vacation, if you don't have anything else to do. So, and the last question is actually these rigid taxonomy structures, what I showed, how can we use that in order to improve learning of constraints from human demonstration? So in the machine learning community or the robot learning community, people would say, how can we use these taxonomies as inductive bias for learning? Of course, I mean, these taxonomies, they are somehow implemented now. How can we make use of them really in order to bootstrap learning task models from human demonstration? I'm almost done. The last part is reproduction. The last part is reproduction. We're not going to talk about that. These are things how we can map these task models. For example, the movement primitives, what we learn to different robots, solving the correspondence problem, but also how we can improve the primitives or the executed tasks based on reinforcement learning methods. I will stop here. If you are interested in going deeper here, you should come to the robotic 2 lecture in the summer term. Yeah, and I will offer it actually online so that people from outside Karlsruhe can join. We have 5 lectures on learning from human observation in the robotic 2 lecture. If you are interested in the summer term, please contact. And learning from demonstration, many exciting and still open research questions. So, for example, how can we generalize beyond training distributions? How can we learn from few examples? And how can we verify actually the correctness of the learned behavior? And maybe at some point, because providing demonstrations from human is costly, and we need humans who have to perform these tasks. And as we know, these days, people are learning in simulation, generating syntactic data, or they're using teleoperation methods, and people are looking into data, internet scale data, like YouTube videos and other, from which we might be able to learn models which are executable in the robot. And I think Georgia, in her talk, in her lecture last week, she described also many directions and areas what's going on here in this field. So with that, I would like to conclude. I would like to thank my team here. Most of them contributed actually to this research, and would like also to thank you for your attention and wish you, of course, all the best. Merry Christmas and Happy New Year, and see you next year. Thanks a lot.
Thank you very much, Tamim. Sorry we arrived late. Are there any questions? Also, questions online?